Welcome back, everyone. I hope you enjoyed lunch. Eileen Rizzo, Associate Director of the Ames Center, and her partners are leading our lunch recess today. They'll be exploring Mobius mysteries. Together, we'll all create a special paper loop and explore phenomena and puzzles with this seemingly simple structure. They will also discuss connections to spatial reasoning and the use of predictions in learning opportunities. Please welcome Eileen and her partners.
Hi, everybody. Good afternoon, and welcome back. My name is Scott Nielsen. I'm from the Ames Center for Math and Science Education in Fresno, California. I think right now we're having just a small technical glitch, and you can't see my face, but you can probably see my iPad camera pointing at some materials here. Here's my hand waving hello. I am here with Eileen Rizzo, also from the Ames Center.
Everyone.
Hope you had a good lunch, and I hope you're ready to play a little bit. We're going to lead you through a little activity, and you need some materials. And I'm hoping that you saw an email that had these materials listed. But if you don't, I'm going to give you just a minute. If you could grab a piece of paper, some scissors, a roll of tape, or a tape of some kind. It doesn't have to be masking tape like this, any kind of tape, maybe even a glue stick would work, and some kind of writing device. I have a marker here, but a pencil or a pen or crayon of any kind will be just fine. And so if you have those, we're going to do some things with some Mobius loops. Now, Mobius loops, and I'm just going to talk for a little bit while some people might need to go and gather those materials. Mobius loops are something that a lot of mathematicians go through and do maybe in their math ed programs, but maybe you've never done these before. These are certainly something you can do with almost any age of child, but I'm really going to invite you to just play along as a learner yourself for the next few moments. I've done these a lot of times, and just about every time I do something with Mobius loops, something surprising happens. So even if you've done these before, I'd really invite you to do it again and play along and see if you have anything that's kind of surprising or new happen. So again, piece of paper, some scissors, tape or glue stick of some kind, and some kind of writing device. And I'm going to go ahead and begin. Eileen is keeping an eye on the questions in the chat, so there are going to be a couple of times that we'll invite you to maybe throw some ideas or questions in there, so feel free to do that. And we're going to start by just cutting some strips of paper. So if you take your paper, and we're going to cut along the long side of the paper, and we're going to look for about 1 inch across. So cut about a 1 inch strip. That's about 2.5 centimeters, 2.5 or 3 centimeters wide. And you can do that 3 or 4 times. Let's make several strips out of our paper. There we go. So just several strips of paper. I'll give you just a moment to do that. While you're doing that, I'll just give you maybe a little background on the Mobius loop. Mobius strips are generally attributed to a German gentleman named August Ferdinand Mobius. However, way back in ancient Rome, in the year 200, they made some mosaics, and there is evidence that they had already discovered the Mobius loops, because in those mosaics, there's some images of Mobius loops. So even though they carry Mr. Mobius' name, these certainly are well known throughout the world and have been for a long, long time. Okay, so the first thing we're going to do is let's take one of these, and we're just going to make a regular loop, not a Mobius loop, just a regular loop. So we're going to take the strip, bring the ends together,
and then we're going to join those ends. So take a piece of tape, and a recommendation here as we make all of these loops, instead of putting the tape parallel with the strip, you're going to want to make sure the tape goes sideways and goes all the way across the strip like this. Because when we're going to do some cutting, and we want to make sure that that joint is taped all the way across. So right now I've just made a single loop, a regular loop. A proper geometric name for that might be a cylinder. And we're fairly familiar with this shape, or this idea. But now what I want to do is just draw a line. So I'm going to start, get my marker here. Let's just draw a line down the middle of this. And as we do that, you can probably predict fairly easily and visualize what's going to happen when I get around to the other side of the loop. So not surprisingly, my mark ends up right where I started. Okay. Now I'm going to take the scissors, and we want to cut along that line. I'm going to take my scissors and just poke right in there. I'm not cutting in from the edge, just begin cutting around. Now also, as we do this, can you visualize, I'm going to stop for just a second. Can you visualize what is going to happen when I complete that cut? And maybe if you have already done it, maybe type in the comment window down below, what happened? Was your prediction true? So not too surprisingly, we end up with two loops, or two smaller cylinders. Well, let's set those aside for right now. And now let's move on to actually making a Mobius loop. Okay. So here's how we make a Mobius loop. We're going to do that same thing. We're going to take these two ends and bring them together. But just before I tape them, to make a Mobius loop, we're going to give a half twist to one of those ends. So again, a normal cylinder would come together just like this. But now I'm going to make a half twist, and now I'm going to tape those together. And again, you want to see if you can make sure you're taped all the way across. Missed a little bit there, so I'm going to bring in another piece of tape. So let's think for a moment. How is this loop different than just a regular cylinder? I just put in that half twist. And it looks quite different, doesn't it? It's still just a simple strip of paper, but different somehow. I wonder if those two things we did, drawing a line and cutting, I wonder if it will react differently. So let's try that. Let's start with drawing a line. I'm going to start at my beginning point, and again, draw a line right down the middle. And can you visualize what's going to happen when we get back to the beginning? Will it be the same? It already looks like something different is happening. Hopefully you can see this okay. So it actually took a lot longer to get back around to the beginning of my mark. Not only that, but I'm noticing that my line is now on both sides of the paper, whereas before, with the regular cylinder, it was just on one side. That's kind of interesting. What that's telling me, so with a regular cylinder, we have a clear outside and inside of the loop. But with the Mobius loop, there's not an inside or an outside. There's only one side, isn't there? Just one side. Interesting. So let's see what happens when we cut. So again, I want to put my scissors here into that line and begin cutting around. Now, as we cut, can you visualize what's going to happen? With the regular cylinder, we just got 2 loops. Is that same thing going to happen with the Mobius loop? If you want to make a prediction in the comment section, that might be okay. I don't know, Eileen, if any of those are showing up there. So I'm going to hold on.
We had some predictions for the first one.
Awesome.
2 loops, 2 cylinders,
Okay.
2 loops that look similar to the first one.
Yeah. Okay. So I'm kind of purposely not letting this go. I want everybody to have a chance to cut. All right. So what do you think? As I unfold this, do we have 2 loops? And we do not have 2 loops. We've just got 1 loop. And it has some kind of twist in it. I wonder if that's the same kind of twist? Or is it twisted more? Or less? Hard to twist less than just a half twist. Looks like it might be a full twist. Interesting, but it's still just 1 loop, even though I cut it all the way around. Kind of surprising. All right, I'm going to kind of pass over to Aileen here. I'll keep demonstrating what she's talking about, but she's going to lead us through some more parts of the activity.
Hi everyone. As we continue our investigation of this Mobius loop, you probably saw the first loop and it probably reminded you of maybe some childhood memories. Maybe you remember making those cylindric loops when you were a child and you made chains for a festivity or to decorate your Christmas tree. Young children at a very young age are used to interacting with paper. And this is one of the first activities they do where they see a 2-dimensional object become a 3-dimensional object. And it's so amazing and interesting to watch children make these loops, to connect them, but also to provide them the vocabulary to express the properties that they see. So on your screen, you see a slide of a work of art from Moritz Cornelius Etcher, better known as MC Etcher. And he's one of the world's most famous graphic artists. He actually left the study of architecture to pursue graphic arts. And during his lifetime, Etcher made 448 lithographs, woodcuts, and wood engravings, and more than 2,000 drawings and sketches. This one, as you can notice or recognize, is one that he presents the Mobius loop. Etcher was really amazed with geometric properties. And I think he really was very successful in conveying that sense of wonder, the sense of imagination that he had with that. His work of art is very recognizable for its style, but it also communicates a lot of mathematics there. And we see him use those ideas that he was interested in to present his work. But the Mobius strip isn't just something that conveys beauty or a sense of wonder or makes us really curious about why things happen and why they don't. It also is very applicable. So this diagram that you're seeing here is the Mobius strip was used by B.F. Goodrich Company in 1957, and they patented a conveyor belt. And they incorporated this half twist because it had an advantage of other conventional belts in that it had a longer lifetime. it would expose the entire surface area of the belt that you kind of experienced right now by drawing a line through it, that it would allow the belt to wear equally on all sides. And so it was really a way to solve a problem and to be able to stretch the budget for the belts that they were buying and replacing and the time that it took to put those on. So while mathematics is beautiful and very intriguing, it is also very applicable. And we see that constantly in the world around us. So let's go back to our Mobius loop and let's continue to explore a little bit. And what I'll have you do is first make a new Mobius strip. Now that we've made one, we're kind of interested in the twist, and we're going to put back that half twist there and put those two strips together. Remembering to put, if you're using tape, you're using that across that seam. And if you're using glue, you want to make sure that you give it a little bit time to dry. So tape has an advantage of making it and using it very quickly. So in what we already accomplished, we saw that drawing a line around the Mobius strip made that line appear on both surfaces of the Mobius loop. And we did that right at the half mark, right in between. So in our next investigation, we're going to do something a little bit different. We're going to change that fraction of 1/2 to 1/3. So you can imagine the width of your loop and breaking it into 3 equal parts. Now, if you can imagine, just eye it, you don't have to be exactly precise and measure, but you can see you can break it into 3 equal sections. And what I'll have you do is extend just one of those all the way through the Mobius loop till you reach back to your beginning point, okay? So Scott here is showing that we're just taking one of those and we're going to take it all across that Mobius loop. And as you do that, I'd like you to think about, even as you're drawing that, how it's a little bit different from going halfway, from going right in the center. Is there anything that you're noticing as you're even drawing that, as you see that those marks start appearing on your paper and continue to find that space of 1/3 from the edge? What are you noticing? Maybe if you'd like to put it in the chat window. Let's see if you're noticing anything even as you're drawing. So as we're drawing this, I just wanted to point out that in mathematics, this type of study, or the Mobius loop, is an example of topology. And topology is concerned with the properties of a geometric object and what properties are still there when we transform it in some way, when we stretch it, when we twist it like we're doing here, when we bend something. And it's something that we really do probably every day. In various tasks that we might have. When we fold up the grocery bags, or when we put something away, or when we open a map that's actually a paper map, we might put some of these things into play. And so it's interesting to look at topology and the different ideas that are there. So as you complete your drawing through the strip and come back to your beginning, now we're going to invite you to start cutting along that line. And we've invited you every time we've cut to kind of start visualizing, what will this look like when I'm finished? What will happen? And so let's just take a little bit step back to the beginning. We had a single loop that was really a cylinder, and we cut it in half, and we got 2 half-size loops, right? 2 half-size cylinders. And we made a Mobius loop. And right down the center, we drew a line and we cut along that line, and we got a loop that's now longer than the one we started with, has more of a length. the twists are not the same. It doesn't look like there's just a half twist there, but it's still a single loop. So I wonder if the 1/3 will make any difference. What do you think? What are you thinking now? So Scott's holding that just a little bit longer to kind of give you some time to do this together with us, and to also give you some time to think about what is your prediction? What are you visualizing that's going to look like? And as you make your last cut, what does it look like? All right, Scott, you ready to unveil that?
All right, here it comes.
Here we go. So we have some in the chat room that said, I thought the first one would have been 2 separate loops, but it would have been intertwined. And this one is now unveiled, and this one is intertwined, 2 separate loops, not equal in size. We have a smaller one there. Looks like a Mobius loop, looks like it only has a half twist. And we have a longer one. It looks like it has more than just a half twist there. I wonder what proportion they are in relationship to each other. And I wonder why one has one set of twists and why one has another. So as we conclude our demonstration here today and the activity that you've been able to engage with us in, I'd like to just invite you to just review a little bit of the components that we've tried to put into our math recess time. We really try to put each of these components in here and want to encourage you to do the same when you think about doing these activities with other teachers and even young children. The first one is we engage the learner with tangible materials. When you're actually doing it with us and not just watching, when you're embodied in that learning, we know that that makes a really big difference. And so we encourage teachers to also be learners, to put themselves in the place of a student as a novice and try something and remember what the wonder of learning really feels like. The second one is utilizing the power of prediction. We know that making mistakes helps us learn more. And when we make mistakes, our brains makes more connections to the new learning when we correct that mistake. So we need to be willing to take that risk of making a prediction and seeing if what we intended to happen or what we thought would happen does or doesn't. And then that makes us even more curious. Why? Why did that happen? Why did it turn out the way that it turned out? Number 3, provide opportunities for problem solving. There's a lot of great questions here, a lot of ways we can actually think about how would we figure out just how many half twists there are in each of these models that we just made, and what would happen if we change the fraction. And what we've done, hopefully, is just kind of start that process, but there's so much more problem solving that can go on in analyzing patterns and analyzing the different sections. That could be very simple for a young learner and then get very complicated for an adult. So it always invites the learner to problem solve. And the last one, to extend and encourage future exploration. When you harness the power of a child's inner attention, when you have them truly engaged, then we know that that sets in motion their continuous curiosity and wonder about the world around them, and mathematics is all around them. And that is such a powerful feeling, not only for an adult to engage in something like a Mobius loop that you might have never heard of, but to also engage in everyday common activities that have been presented throughout this conference about places and ways that we can engage learners to see that and to express that, to value their thinking behind that, and continue to grow. So we'd like to thank you for joining us today for this math recess. And we want to tell you that we have a lot more resources around the Mobius loop. We have a blog that was written around the history and some more investigations that you can explore. We have a one-pager document that aligns with the activity that we just did with you, with some questions and what to look for, materials that you need, so that you can share this with others and integrate it in your own ways as an educator. And we invite you to continue to explore our website for other resources that model these same components that we've modeled here, and to join us for any future events where we try to harness this active, embodied, playful style of learning around mathematics and truly change the narrative of what it has been a stereotype that's been for mathematics, and in realms where it doesn't value an inclusivity and it has this very procedure robotic spaces to just break that stereotype and to really make it playful and enjoyable. So on behalf of the AIM Center and Scott and I'd like to thank you again for joining us, and we hope we see you in the future.
Thank you, everybody.